the next type of annuity, the ordinary annuity, and that's the one where we make our deposit or payment, if you like, at the end of the compounding period. So it's more like loans rather than investment. The future value would then be, and it would end up being a series, but slightly different to the other annuity, because now it'll go P plus PR squared up to PR n minus 1. So it's our traditional geometric series. P is again our principal, and R the 1 plus interest rate, and so on. And so to work out present value is the amount I would put in now, just one lump sum to get the same future value. PV is P outside of 1 minus R to the negative n on R minus 1. But again, we don't really use those. We tend to build it up. We'll talk about repaying loans. Key idea, the amount you've still got owing after n time periods is that. It's always going to be that. The principal, or the amount I've borrowed, plus the interest applied to it, minus all the instalments I've made with the interest applied to it. Use this example. Borrowing $20,000 from a bank, interest is 12% per annum, compounded monthly, and we start repaying the loan at the end of the first time period. Makes sense. Why would you pay back at the start? That doesn't make sense. Borrow all this money on here, have some of it back straight away. No, that's always at the end when you're paying back. How much will they owe at the end of 6 years? So we've got to look at, first of all, the principal. The principal, but only for 6 years at this stage, but that's 72 months. But you've got to think about repayments are like an investment, a reverse investment. See? So the initial loan, that is like the bank investing in you. So they're giving you this money, right? So it's like they're making an investment in you, but they're going to make interest out of it. So it's like they're making an investment. Your repayments are investments in the bank. You're going to give them money. The first repayment will be invested for 71 months. Then the second repayment for 70 months, and so on, until you get to the second last one, which will just be there for 1 month. And the very last repayment is invested for 0 months. Because it's the last repayment, everything's paid back, it's all done. And so the difference between the two is the amount that would still be owing. And again, we created our geometric series, which we can calculate, and then we can see $9,529.01. And you better believe they'll chase you for that 1 cent. So how much interest have they paid in those 6 years? They've made a total number of 72 repayments of $300. So they've given the bank $21,600. They've reduced the loan by $20,000 minus $9,529, because whilst the total repayments are $21,600, there's still $9,529.01 owing. So they've only reduced the loan down to this balance, $10,470. So even though they've made $21,600 worth of repayments, the loan's only been reduced by $10,000. The difference, therefore, must be the interest that they've paid. So all up, they've paid so far $11,129.01. What about if the problem was you had to find the amount of each instalment? And this often happens, right? You might want to borrow some money for something, and you say, well, I know what the interest rate is, and I want to pay it off over 5 years, but you want to work out how much will I pay. So this is what I want to work out, is how much I'm going to pay back. Monthly installment's going to be $M. Now that initial loan is borrowed for 60 months. So the bank is investing in you, they're giving you $30,000 and letting you have it for 60 months. Then I'm going to give some money to the bank and let them have it for, well, the first one they can have it for 59 months, the next one 58 months, and so on, until I give them the last one. And they go, here you go, we're done. So the amount N will be the principal with the interest applied minus all those instalments with the interest applied. But the difference with this one is we know what amount 60 is, because that's when the loan's paid off. So it's going to be 0. I just got to make M the subject, and then I know what the monthly repayments are going to be. So playing around with all that, there we go, eventually $622.75 a month. Maybe we've got a different situation. we want to find the length of the loan. So this time we know how much we're going to borrow, we know what the interest is, and we know how much we can afford to repay. So we want to know how long is it going to take. They're going to borrow, how many zeros there? They're going to borrow $3 million at the beginning of 2005, interest rates 12,000, calculated the balance each year. The debts to be repaid, annual repayments of 480,000. First thing was just to show this is true. Okay. Well, that initial loan is borrowed for 2 years, so there's $3 million with the interest rate applied. First repayment, that'll be in there for 1 year. The second repayment, and that's all they're really asking for this one. So it'll be the principal plus the interest minus the instalments, and we should be able to manipulate that. All we've got to do is, change it into scientific notation, and we got it. Show that amount n turns out to be that expression. Okay. Well, this time it's to the power of n, and so it'll be there for n minus 1 years and so on until we get to the last one that's in there for 0 years. And there's our geometric series. All right, we'll get there. Now, that wasn't quite what they asked for, was it? So we're going to do some factorising, we'll get it. If I expand that out, those numbers worked out nice, didn't they? Who knew? 480,000 divided by 0.12 comes out to be exactly 4 million. They've taken out a common factor of 1 million, but we get there. In which year will they make that final repayment? So when will AN equal 0? I've got an expression for AN, so we've got, well, it's going to end up being a log equation to solve. Okay, the 13th repayment. So that will be at the end of 2017. Something a little bit more recent. Tina inherits $60,000, invests it in an account earning interest 0.5% per month. But then each month, immediately after the interest has been paid, she then withdraws $800. The amount in the account can be worked out using this recurrence relation. So they haven't actually asked us to show this, they've given us that information. Using it, find the amount of money in the account after the third withdrawal. Well, A3 will be A2 with that 1.005 minus 800. But of course A2 would be A1 times the interest minus 100. But then A1, so eventually we get down to A0 times 1.005 cubed. They told us A0, there it is, 60,000. And we have the amount. So what was the amount of interest earned in the first 3 months? There it is. Where'd that all come from? Okay, so that's the balance we just worked out. But we've also taken out 3 lots of 800. So that was money that we got. Take away the principal, because obviously that's not ours, that was theirs. The difference must be the interest. Calculate the amount of money in the account immediately after the 94th withdrawal. So A94. So what I did was I said, well, look, if A3 was that, I can see the pattern. I'm not going to redo the whole thing, but logically A94 must end up being an expression like that, using that pattern. That gives me a series I can play with in the other one, and we get the amount. See, I didn't bother with creating a series up here because there's only 3 terms. It's easy enough to just bung in the calculator and get the answer. Whereas this one, I need to use the series because who wants to put in 94 of those terms? And there probably was some that did, mind you, but just a handful of questions there to look at.